Okay, so we're going to continue our discussion of electromagnetism, Physics 210, with something called the displacement current. So let's talk about displacement current. Okay, so let's consider the following situation. Okay, let's draw a picture here. I'm going to draw a wire. That's my wire right there. And in this wire, I'm going to put a current I flowing through this wire. Okay. Now, um, I'm going to do the following. I'm going to make this wire really, really, really long. And far, far away, I'm going to put a parallel plate capacitor. So I'm going to basically draw a parallel plate. This is be circular parallel plate. It doesn't really matter, actually, for the purpose of this discussion. Okay? Parallel plate capacitor. And then this current just keeps going on. All right? Okay, so I'm pumping some current in this direction. And I know if I basically do Ampere's law, all right, I can basically try to figure out the B field here. Right? So let's do the B field here. Okay? There's the B field. All right, that's my current. That's my C, and I can use Ampere's law. Ampere's law says following. So okay, so let's so find B field using Ampere's law. Okay, and that's just basically integral over C of B dot dl is equal to mu 0 IC, where this is the current flowing through surface enclosed by C. Okay, so that's the surface that's flowing through. So I can imagine that this surface here is this thing right here, and you can see basically the current flowing through this thing is just going to be I, right? This is ultimately going to be mu 0 I for that surface there. Okay. All right, and you could argue basically, so this is non-zero on this side, and this is basically some integral, and then you could argue that it's axially symmetric. You spin this thing around, you can get B dot times L, and you get the B field there. Okay, so nevertheless, there is some B field here. Okay, now this is the key piece, right? It says current flowing through surface enclosed by C. How many surfaces are enclosed by C? Well, there's the obvious one. There's this one. But in fact, there are infinitely many of them. So for instance, I can imagine that if I open this thing up, that there's another surface that looks like this, right? So you can imagine it's like a ball, all right, with basically a hole at the top, right? That's a surface. This is a surface here enclosed by C. Now, this doesn't change anything yet because still there's some I flowing through the surface right here, right there. But let's suppose I make it really big. And now imagine I go through the parallel plate capacitors, all right? Now I have an interesting conundrum. What's the conundrum? So for this surface, I'll call this S prime here. Okay. If I use Ampere's law, so if I take surface as S prime, what I get is that implies that mu 0 IC is equal to 0. Why is that? Because there's no current flowing through here. Look, there's a break in the wire, right? There's a capacitor there, right? So if there's no current flowing through here, right, that implies the integral of C over B dot dl is equal to 0. So this is not true as that. This is not part is not 0. This part is 0. And the only difference is that C is the same. I'm just choosing a different surface for both of them, right? In this case, I chose the obvious surface, which is usually what you want to do. In this case, I chose a non-obvious surface, which is fine, right? There's nothing forbidding you from doing that, okay? So what that means is that basically, I'll call this surface here S. So S and S prime have the same boundary, right? Which is C, all right? Okay. But I of S is equal to I, and I of S prime is equal to 0. Okay. So what that means is that the physics is inconsistent. Okay. And when it's inconsistent, that means you're missing something. Right? Because there's one thing that's important for physics is that basically no matter what the situation is, you have to get the same result, right? If you're getting different results, that means you're missing some critical piece. All right? Okay, so some physics is missing. We're missing something. Let's talk about that missing something. And that missing something is actually going to be the displacement current. All right, we're going to talk about that today. Okay, so let's go ahead and talk about what the displacement current means. All right. So what is different about this situation is that as this current is flowing in, there's actually something happening here. It's not like nothing's happening. What's happening is that charges up are building up here, Q and minus Q, right? So charges are building up here. And so the E field is strengthening here. So basically growth of E field, okay? So I'm going to define another term. I'm going to define a new term. So define another term. I'll call this ID is equal to epsilon 0 d phi E dt. So this is the electric flux, right? Because that is changing. Actually, I'm just building up my electric flux, right? This is basically the permittivity of free space, right? And I'm going to call this basically the displacement current. Okay. All right. And so the displacement current right is the change in the E field. Okay. All right. So let's go ahead and do this, right? So we're going to basically write down. So we need to write down. So we need to include this. Include this in Ampere's law. All right. So it's something called generalized Ampere's law. Okay. So let's go ahead and show that what's out. So basically, we're going to have something called the generalized. Let me put this over here. Square this up a little bit better. Okay. Generalize Ampere's law. Okay, and you can probably guess what that's going to look like. So it's going to integral of C B dot dl. That never had a problem basically. This is going to be equal to mu 0, right? I C plus I D comma C, right? Which is going to be equal to mu 0 IC plus, basically, this is the regular part, plus mu 0 epsilon 0 d phi E dt. Okay? So this is the extra term here. This is the extra displacement current. Okay? Okay. So for our previous case, okay, so let's basically remind us of what the previous case looked like. So that's our previous case. All right, in that case, you have basically some E field is building up there. Okay. Let me see if I can basically do this so that we can see it all at once. Phi E is integral of E dot dA, which is what, right? 1 over epsilon 0 Q enclosed. All right? This bad boy right there. Okay? Right? And so what that means is that d phi e dt is equal to 1 over epsilon 0 dq enclosed dt, all right? This is just 1 over epsilon 0 times I, right? Because I is just basically the amount of current that's being pumped in this thing. This thing's increasing in function of time by how much? By I, okay? All right. So then basically for S prime, so for S prime, the generalized Ampere's law gives, right? Let's see how we want to do this. Right, let's do it this way. So basically, we're going to get integral over C B dot dl is equal to mu 0 IC plus mu 0 epsilon 0 d phi E dt. Okay, so this part right here is a 0. Why is that? Well, basically look again. There's no physical current flowing through there. Okay? Plus the second part, this is going to be mu 0 epsilon 0 1 over epsilon 0 dq enclosed dt, right? That's the buildup of charge on one of the plates right there. And of course, this is going to be equal to, the epsilon 0's cancel out, mu 0 to q enclosed is just I. And now, basically, all right, this is now consistent now, right? So this is now consistent. So now this is consistent, right? And so basically you need to include this displacement current. All right. Okay, so now let's basically put all the laws together. So we worked out all the laws. So we worked out all the laws of electromagnetism. Okay, so let's write them down. Okay, so write them down. Okay, so we have a bunch of these laws. Let's go ahead and write some of them down. Okay. All right, so let's go through each one of them in turn. Okay. So the first law that we have is the following, basically. This is integral of E dot dA is equal to Q enclosed over epsilon 0. This is known as Gauss's law. I don't know, with an S. Okay, that's the first one. Okay. Second one, B dot dA is equal to 0. This is Gauss's law for magnetism. This is a fundamental quality. This basically says there's no magnetic charge. That's what that actually means. All right. Next one, okay. We have basically another one we worked out. Integral of integral of E dot dl over some contour C is equal to minus d phi B dt, right, which is equal to minus integral of, actually I should be very careful, actually minus d by dt of the integral of B dot dA. Okay, so this is known as Faraday's law. Okay, so this I should mention, this is S. S is some closed surface. right? And this one is going to be S. This is going to be surface defined by C. This is open surface, right? Because it has the C defines the boundary around this. These closed surfaces have no boundary, right? Like a sphere or circle or something like that. They have no boundary. Okay. Why is it so bright? Maybe I'll turn this thing off. That's a little better. Huh? It's like it's just weird all the time. It keeps changing my lighting situation. All right. And then last thing we just basically came up with is generalized Ampere's law. Integral of C B dot dl. You can see the symmetry, right? This is integral of E times dA. Oh, sorry. This is integral of E times dA, B times dA over some closed surface. This is integral of E times dl over some closed contour C over some contour. Basically same thing, B dot d over some contour. This is going to be equal to mu 0. I'm going to turn the light back on, see what this looks like. And then turn it all the way down. Yep, it's like I have a sleeping light here. Sleeping light. No, that's crappy. Study light. Yeah, it's a little better. I just don't know. Okay, is equal to basically IC plus ID comma C, right? Where this is Ampere's law. More general, it's called the generalized Ampere's law. And then ID is equal to epsilon 0 integral of basically d phi e dt, right, over the surface. No, this is it. That's just sorry. This is ID is equal to epsilon 0 d phi e dt. That's just it actually. Okay. All right. So that is it, right? So you can basically have Gauss's law. All right. You have Faraday's law, Ampere's law, and Gauss's law for magnetism, right? So these are 4 laws of electromagnetism. We spent our entire semester basically just writing this down, this down, this down, and this down. All right, that's it. That's it. There's only 4 equations in all of electromagnetism, right? Okay, this is why you could write this stuff on a t-shirt, right? And it's why it's so important, right? It's like the entire basis of our modern society is enclosed basically right here. Everything dealing with electricity and magnetism is this it. That's it. Radio waves, lasers, blah, blah, blah. All that stuff is right here. Okay. This is it. Okay. Now, there is a more common form that's just written. Okay. This is more in differential form, right? So this is in differential form. Okay. That's basically del dot E is equal to rho over epsilon 0. This is the charge density. Okay, there is basically del dot B is equal to 0. This is basically del cross E is equal to minus dB dt. And then del cross B is equal to mu 0 J, that's a J, plus epsilon 0 dE dt, where this is the current density. Okay, and of course you've seen this written in many t-shirts throughout the years, right? This is like called Maxwell's laws, right? So these are Maxwell's equations. Right, and they basically enclose all my electromagnetism. Like Maxwell equation, you can write like this, or you can write like that. Okay, this is integral form, differential form. This is what you usually find in t-shirts. You find this in a t-shirt, buy it. It's rare. It's awesome. Okay, all right. So what is interesting about Maxwell's equations, like when James Clerk Maxwell first wrote this thing down, he's basically found that they obey wave solutions. So Maxwell's equations admit wave solutions, right? This is really important, right? Because basically without it, we have essentially nothing in the modern world, right? Let me make sure I got everything there. Okay, great. Okay, so what is a wave solution, right? So the wave equation, right, is, okay, d squared f dt. I'll write it like this: d squared f dx squared is equal to 1 over v squared d squared f dt squared. Okay, that's the wave equation, right? This is, so any equation looks like this. So the solution is f is equal to basically some function f1 x plus vt plus some function f2 x minus vt. Okay, that's it, right? Where these are just some arbitrary functions. Okay, then that's it basically. Just these some arbitrary functions, as long as they're differentiable, basically. What you can do is basically write this like this, and then plug it in. It will work every single time, right? And these have physical meaning. So this is what's called a left moving wave. And this one is what's called a right moving wave. Right? Assuming basically x points from left to right. Okay. Okay. So I won't derive it, basically what these equations are, but for E&M, electromagnetism, you can show Maxwell's equations give two equations, and these are the two equations, right? D squared E dx squared is equal to 1 over c squared d squared E dt squared, and then this one is d squared B dx squared is equal to 1 over c squared d squared b dt squared. Okay, now you might notice that like I'm writing the d as this little script d, right? This actually means partial, right? These are partial derivatives. For the purposes of this class, it won't matter to you basically whether these are d's or partials, right? Eventually it might, okay? But for now, you don't have to worry about this sort of stuff, right? It's just extra complexity you don't need to worry about, okay? All right? Okay. Now this thing's interesting here. This is a constant here. C is the speed of light, right? And it's defined by, okay, speed of light or the speed of wave. Okay. Formally, it's actually the speed of wave. You actually don't know what the speed of light is, right? But once you compute this thing out, you will find out what it is. So C is equal to 1 over square root of mu 0 epsilon 0, okay? Which is, if you plug the numbers in, 3 times 10 to the 8 meters per second, right? So that's the speed of light, basically, right? Okay. Okay, and this wave, these waves, are the basis for electromagnetic radiation, right? Okay, or light. We call it light, but it's actually radio waves, everything basically, microwaves, like X-rays, blah blah blah. All this falls in Aegis electromagnetic radiation. And then, like always, they have frequency and wavelength. And the frequency and wavelengths are related to each other. Okay. All right. So let's see. I should make a little plot of all the different frequencies and wavelengths. All right. So I'm gonna make a little table right here. On one side, I'm gonna put the frequency. Okay. And on the other side, I'm gonna put the wavelength. And I'm gonna start from high. So this is in hertz, right, or seconds minus 1. Okay, and I'm going to put a name in the middle, okay, for the type of radiation it might be. So I'm going to start out really high, 10 to the 23rd, okay? This wavelength is something like 10 to the minus 12, right? These are called gamma rays, okay? Then a little lower is 10 to the 20, right? Okay, these are called X-rays, okay? You go to the doctors, but you get X-rays, right? Then basically around 10 to the 17 to about 10 to the 16, this is called ultraviolet, UV, right? And so basically around here is about 10 to the minus 9 or 1 nanometer, okay? These are basically computer chips. Roughly the size of the features on computer chips basically make things go in the world, all right? The record right now is 7 nanometers, right? But they're trying to push it down to 5 and less, right? Every nanometer go down is like several $billions actually. Not in terms of buying a chip, but in terms of the facility that makes it. 10 to 15, that's light. Okay, this is about 10 to minus 6, I believe, right? Meters. Is that right? It's a few hundred nanometers. That's about right. So it's maybe 10, close to 10 minus 7. 10 to 14 to 10 to 12. This is called IR, infrared radiation. Okay, it's roughly around 10 to minus 5 meters or so. Right. Basically, as we get higher and higher, what we get is around 10 to 12 to 10 to 10. These are microwaves. All right. And then 10 to 9, this is Wi-Fi. Okay, Wi-Fi is actually between 10 to 9 and 10 to 10. It's like 2.4 gigahertz, right? So it's like 2.4 or 5 gigahertz, right? Cell phones are here as well. This is around 10 to the minus 1, okay, meters, right? And then what we have here is we have 10 to the 8. Okay, this is FM. For those of you who know what a radio is these days, okay, radar, right, plus TV, okay, it's about 1 meter or so, okay, all right. Why 1 meter? Well, radar works in this range partially because basically airplanes are roughly the size of humans, right? Or all the features on airplanes are roughly the size of humans. So 1 meter things will detect airplanes, basically, right? You could detect them with smaller wavelengths, but it requires more power, and then like sometimes it gets interference, basically from raindrops and whatnot, right? So you like radar to be slightly longer, okay? This basically keeps your food hot, all right? This is what you emit. IR radiation is what you emit, basically. And then light is basically what you see, right? It turns out light, the reason why we see light in this region is that we have the sun, not close to the sun is there, right? And because the sun is there, its peak luminosity is actually in the visible wavelength. That's why basically our eyes have adapted to see the brightest part of the sun spectrum, right? Turns out. Okay. All right. Yeah. So if we lived around a different kind of star, right? Say a M dwarf, which is one of these low mass stars, which are much dimmer and cooler, our eyes probably would adapt to see something in the IR, so we'd probably see more heat and stuff like that. If you see around even hotter star, probably would adapt to see UV or whatnot, right? So it's basically this is a biological reason why we actually see light mainly. All plants absorb light as well. Okay, so that's basically the hierarchy of different wavelengths. You can see it goes from 10 to 23 down to 10 to 8. It actually goes lower than that if possible, right? But you can see just in terms of basically what humans usually have access to, right? 10 to 8, 10 to 23 to 10 to 8. What's that? How many orders of magnitude? 15 orders of magnitude? That's a lot. So that's 10 with 15 zeros behind it, right? Okay, so let's see what I want to do here. Right. Oh, I see. Okay. So we're going to do a few examples here now, all right, of like what it might mean, all right? So let's do this. Let's consider a simple example, all right, of displacement current. So let's consider a simple example of displacement current. All right, and this relates back to a problem we run previously, which I always said was basically not what's the right word? Not really. It's not relevant. It's just that like it's not really physical, right? Okay. And we're going to revisit that in a slightly more physical context. So this is the following situation. I have a current I flowing through the wire, right? It's very similar to what I did before. And I have a parallel plate capacitor here. This parallel plate capacitor is a circle of radius R. I have another parallel plate capacitor here, at least the other part of the plate going at, also basic radius R as well, right? And I is flowing out this way. So I flows in, I flows out, and there's some electric field that builds up between these two. So this is the E field here, okay? All right, so here's the problem I have, right? I want to calculate the B field between the plates. And I'm going to ignore fringe effects. Okay? So, what do I do? So what do I have to do is basically write down generalized Ampere's law. Okay? So let's write that down. So generalized Ampere's law looks something like this. Integral of B C dot dl is equal to basically mu 0 IC plus IC comma C. All right. So there's a displacement current. There's a current here, and I'm going to do it between the plates. So in fact, there's no enclosed current here, right? Because there's no current flowing through. So I'm going to draw my circle here. This is going to be radius R. Okay. And again, basically, this is going to be easy. This is going to be hard. Okay. And because this is easy, you can make the arguments on this side. This has to be something like some constant b times 2 pi r, right? That's how that argument works. This is going to be equal to, now you have this piece right here, mu 0 I d comma c, right? So that's the hard part, which we got to figure out, right? Okay. Well, let's try to figure out what this thing looks like, all right? So what we care about, right, is that we care about what's happening in between here, right? And so what we can do is that we need to figure out what the electric field is going to be like. Let me think, what's the best way of doing this? Right, let's do it this way, okay? So what we have is that I d comma c is equal to integral of, let me write this down. This is basically 1 over, it's epsilon naught d phi e dt, okay? And this is basically phi e is equal to integral e dot dA, which is equal to q enclosed over c over epsilon 0, okay? Let me draw my surface here. Okay, so I need to find the electric field. So the electric field is going to be pointing straight that way. There's no electric field on this side. I just need to worry about this piece. So this piece here is just going to be E times basically pi little r squared, that's this piece right here, is equal to Q enclosed, which is the Q in here, right? okay, times epsilon 0. So it's going to be basically be Q enclosed over epsilon 0. And what is that? Well, that's just basically the fraction of the charge that's in here. So that's just going to be basically be Q, which is the total charge on this thing, okay, times pi r squared over pi capital R squared, okay, all right. So that's this piece right here, right? E times A is that, whatever. I don't need to figure out what E is going to be. I just need to know what this piece is going to be, okay? So this is phi sub E. I need to do d by dt of phi sub E. So d by phi sub E dt is equal to, well, there's epsilon 0 here. That's going to be an epsilon 1 over epsilon 0 times dq dt times basically pi r squared over pi capital R squared, okay? And this thing is just I, okay? So you plug this thing in, this is going to be equal to mu 0, okay? Epsilon 0 times 1 over epsilon is going to be just give you 1 times I pi r squared over pi capital R squared, okay? And then basically the problem is essentially done now, right? I hate to write it too small, but we're going to do something like this. B is equal to mu 0 I over, let me just make sure this is right. This is over 2 pi. And this is just going to be a R over capital R squared, okay? Now, for those of you who remember, this is the exact answer that you would get basically when you were considering the following situation. You had some conductor of radius r that was pumping some current through this thing, okay, all right, and you want to find what the magnetic field was inside this conductor, all right. And I always said that this problem was not relevant because in a conductor, all the charges are conducted on the surface of the conductor. Nothing's conducted inside, right? Right? But you have to basically make that leap of faith that that actually had to happen, right? So that is actually the reason why we are doing this, why we did this problem, because this is exactly that. Rather than thinking about the current being equally distributed through the conductor, which doesn't happen, what we're actually looking at is the displacement current, which is a change in electric field in a gap between two capacitors, which does happen uniformly. Okay, so that's basically one interesting thing about that tidbit. Okay, all right, so that basically closes it for displacement current. All right, now what I want to talk about is something slightly different. All right, I want to talk about basically the production of EM waves. All right, so let's talk about how we produce electromagnetic waves. All right, so produce EM waves. Okay, so there are several ways for which you can produce EM waves. So several ways of producing quote unquote light. Okay, light is just shorthand for EM waves, right? So there's a few things which you can do, right? Let me see how I want to do this, right? Right, let's do it this way. Okay, so there are several ways, all right? So ultimately, okay, all EM waves are produced by accelerating charges. In a very broad sense of the word of accelerating, okay? Very broad sense. Okay, let me talk about some of them. Okay, so they are thermal. What produces thermal? So basically hot stuff. This might be the sun. This might be light bulbs. It shouldn't be any quotes. It's actually the sun, right? This is the old function light bulbs. You had a filament in there, it got hot, that glows, which you can't buy anymore because they're just horribly inefficient. There's line radiation. So these are atomic transitions. Right? If you have single frequencies, and it's coherent, okay, these are called lasers then. Right? And then there's also antennae. Let me write that around. A-T-T-E-N-N-A-E. Antennae. It's called dipole radiation. Not exactly dipole. Depends on the antenna, right? But the simplest antenna are all dipoles, right? And so they basically produce electromagnetic radiation as well. Okay, we're going to talk about this last piece because there's usually the most instructive for this purpose, right? So antenna might look like this. Two wires, right? Current flows in, current flows out, all right? And so what happens is that it builds up maybe positive charges on the bottom here, negative charges on top, okay? And basically the electric field will go basically from top to bottom, right? So this is the E field, right? And then sometime later you switch the current around so that basically it goes positive here, negative here, and then the electric field basically goes down again like this, right? So now basically if you switch them back and forth, what happens is that the wave comes out like that, right? And this wave moves away at speed c, which is 1 over square root of mu 0 epsilon z, which is also the speed of light. Okay. Let's see. I want to say with this thing. Right. Right. Okay. So let's do it this way. Okay. The intensity duration depends, right, on the angle, right? So for instance, basically, if you have an antenna like this, and you're basically seeing at some angle, theta, right? Okay, there's your other antenna which will receive it. Okay, the E field at the receiver is basically, so you can imagine what this is. So this is the angle here now, right? This is going to be E0 sine theta, okay? Right, so it's basically the sine theta, right? So the intensity of radiation is I is proportional to sine theta, okay? So this actually has relevance to your life, okay? Why? If you have in your home a Wi-Fi router, that's your Wi-Fi router right there. A lot of the good Wi-Fi routers have antenna flying out of them, okay? You don't want to angle your antenna like that, okay? You don't want to do that, okay? Why? Because what happens is that you only receive basically in one certain frequency. Depending on the orientation of your computer, stuff like that, it's not ideal. What you want to do is that you want to orient them so that there's like a 90-degree block right there, right? And that basically, depending on whichever direction your stuff is oriented, you always receive the better signal, okay? So if you have your laptop computer, the way the antennas work there is that if you have a laptop computer, so your laptop computer right here, blah, 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 okay, your screen right there. If you actually open up these things, the antenna is around the outside of it. It's like a square, right? And basically there's 90-degree bends in it, right? so that you can receive signal independently, like basically at any angle, basically with respect to this laptop, right? So that's one important tidbit here, right? So it's like if you get crappy Wi-Fi reception, go check your router. Basically, just bend the antennas out, and you might actually get improved Wi-Fi reception, right? Okay, so that's a what's a tech tip, all right? Okay, now let's recall the energy density of B fields, density of E fields, right? What is that? That's basically mu E, actually not mu E, UE is equal to 1/2 epsilon 0 E squared, okay? I want to say this, okay? And basically E, well, other than the sine theta here, goes like E0 cosine omega t, right? Because basically this is a wave, right? This is a wave, right? And so basically what you have is UE is equal to 1/2 epsilon 0 E0 squared cosine squared omega t, right? You have a term looks like that, okay? And so when you want to get what the average power is going to look like, this average power, so UE average, well, that's just basically integral of this thing, 1 over t, 0 to t, 1/2 epsilon 0 E0 squared cosine squared omega t, where this is just going to be 2 pi over omega. You've done this integral so many times that you know when you do this thing with respect to t, that cosine squared omega t will just turn into a 1/2, right? So that's just going to be a 1/2 times a 1/2, 1/4 epsilon 0 E0 squared, okay? Okay. Now similarly, for right, for B field, okay, this is going to be equal to U of M or U of B is equal to 1/2 B squared over mu squared. That's just 1/2. Turns out the magnitude of B is just basically E0 over C. So this entire thing squared over mu squared. So that turns out to be 1/2, basically, epsilon 0 E0 squared, okay? Because C is equal to 1 over square root of mu 0 epsilon 0, and the 1 over that basically brings a mu epsilon 0 on the top, and so you end up getting something like this. Let me make sure that's right. This is not mu squared, it's just a mu, and then that works out. Okay, so that's basically, again, UB average, right, with just being another cosine square omega t. That's just, again, 1/4 epsilon 0 E0 squared, right? And so the average power, U average, is U average of the electric field, I'll call it E average, plus UB average. That's just going to be equal to, basically, a few ways of writing it. It's going to be just 1/4. 1/4 plus 1/4 is 1/2. Epsilon 0 E0 squared is also equal to 1 over 2 mu 0 B squared. And that's also equal to 1/2 E times B, E0, B0, divided by mu 0 C. Okay, so there are 3 different ways of writing the same thing. Okay, now make sure everything's there. Okay, now what do I want to say here? Right, so one, let me just see how much more stuff I want to go through. Blah blah blah. Okay, good. Yes. And then like two other things. All right, I will probably skip the solar cell stuff. All right. No, I'll go through. So I won't do the laser cell. Okay. Right. So the intensity of radiation moves out at speed c, right? So there's some energy density here. So I should write energy density. Okay. This is some energy density. This stuff is moving out at speed c, right? And so basically you could write down this is going to be equal to I is equal to mu e, average or something like that, times c, which is just going to be in units of basically, so this energy density, this is energy over a volume, right, which I'll write as meters cubed, okay, times the speed, which is meters times seconds, which is basically some units of energy over seconds times 1 over meter squared, right? Okay. Now, I can write this as I is equal to, U average times C, which basically if you take this piece up here now, it's just going to be 1/2 E0 B0 over mu 0. And I'm going to call this something S average, okay? And I'll tell you what S is. S is going to be equal to 1 over mu 0 E cross B is the pointing, with a funny way of spelling pointing, vector. All right? Okay. Okay, great. All right, so let's talk a little about this, how this energy flux basically propagates through space and time. Okay, now the energy flux. Okay, so let me imagine, so I is just some intensity of some energy field radiating out from something, right? So let's imagine I have some energy field that's radiating out from some point source here, say the sun, for instance. Okay, and I know that the flux going through here, I dA, and the flux going through here, integral I dA, right? If nothing's happening, nothing's absorbing this thing, these two have to be equal to each other, all right? So then what I get is this is going to be equal to I, I'll call this basically 2, and this is 1, and that way I'll call this R1, and this one is going to be R2, okay? So I2 times 4 pi R2 squared, and this one is I1, the intensity at position 1, 4 pi R1 squared. These two, so imagine 3D surfaces, have to be equal to each other, right? Okay, and so what you get up getting is that this implies that I at R1, which is I1, is equal to I at R2 times R2 squared over R1 squared. Okay, and so what this implies is that I is proportional to 1 over R squared. Okay, all right, so now let's recall for dipole radiation. Okay, all right, that basically what we had was that we had basically, it was going to be epsilon 0 E0 squared. It's a 1/2 out in front or something like that. Okay, this is UE. Okay, all right. If I multiply this times C, this basically gives me I now. Right. Now this thing depends on the sign. So this actually goes like 1 over 1/2 epsilon 0 E0 sine squared theta, because I'll write E goes like E0 times sine theta over R squared. Okay, and so for the intensity of dipole radiation, this is proportional to, well, I'll write like this, is equal to L, right, times sine squared theta over R squared, where this is the luminosity of the dipole, which is just the total amount of power being emitted. So this is basically in watts, right? Okay. So, I'm gonna basically tell you something that's a lie, all right? But it's a lie so that like your life is not horrible. Okay. So here's a lie. Okay. So we'll do an example here. Okay. So consider a transmitter emitting at 100 watts. Okay. All right. It's not atypical for a lot of transmitters. Okay. So now basically, what is intensity? What is intensity at 100 meters away? Okay. For theta equals, okay, so it's A, 90 degrees, B, 45 degrees, C, 0 degrees. Okay, let's go ahead and do that. All right, so basically for this one here, I is equal to L sine squared theta over R squared. We'll choose A and B. You can figure out what C is going to be. All right, so if that's true, basically the first one is going to be, let's write this down, 100 watts. Sine squared theta is sine squared of 90 over 100 meters squared, right? And that basically turns out to be 0.01 watts per meter squared, right? This is 100 divided by 10,000 is 0.01, okay? That's A. For B, I is equal to L sine squared theta over R squared. This is 100 sine squared 45 over 100 squared. So this is going to be sine of 45 is 1 over square root 2. Sine squared is going to be 1/2. It's going to be equal to 0.005 watts per meter squared. Okay, this is not completely true. What you have to do actually to get the luminosity is that you know the total emission is 100 watts. You have to integrate it over all sine theta, blah, 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 do that. You know something? I'm not going to press you on that. Just keep it simple like this. Okay. All right. And then, right. Now, you got to be a little careful here, right? Because this thing, when I mean 90 degrees, all right, it really means like basically this angle is 90 degrees, okay? But a lot of times, basically between antennas, but a lot of times, basically, you might actually be given in terms of basically this angle being 90 degrees, in which case it can be 90 minus that. So for instance, what you have to do is to check it. If you're above the antenna like this, where this angle between where the antenna is broadcasting and where you are is 0, then you have no radiation there. Okay, no intensity there. Okay. Last thing I want to talk about, right, and this will be the final example as well, is that light also exerts a pressure, right? So you don't actually feel it. So light exerts a pressure or it carries momentum. Okay? And that means what that means is that light carries momentum and you reflect light, you will feel a pressure from the light as well. Okay? So let's go ahead and talk about this. So let's imagine that this is a simplified way of doing it. Let's imagine you have a particle here, mass m, moving with some velocity v. Okay, the energy of that particle is just going to be basically 1/2 mv squared, which is just basically 1/2. This is some momentum p squared over m. Okay, which is also you can write as 1/2 p times v. Okay, you write several different ways, right? Okay, and so what you can do is that basically you can write p is equal to 2e over v. Okay, now for light, p is equal to e over c. Okay, so you can see the mapping, right? V is the velocity of light, that just goes to c. E is basically just the energy of light, that goes to e. The only thing missing is the 2, and the reason why is that light is relativistic, and so you lose that factor of 2. All right. Okay, I won't go into details. I'll just motivate basically why this is in fact true. All right. Okay. So let me try to think what I want to say here. Right. Okay. So E is just the integral of I, the intensity, times the entire area. Okay. Right. And so basically what you have is that the force, okay, let me try to think about the right way of doing this thing. Right. So if you say you absorb this light here, so you have some light coming in, and then you have the perfectly black surface, so everything gets absorbed here, right? Then what that means is that basically the amount of energy absorbing there is going to be equal to right. Here's the issue, right? This is not E. This is actually E dot, okay, because it's per unit time, right? So what that means is that the amount of energy absorbing there, E dot, is equal to I times A, right? Which means that P dot, right, is equal to E dot over C. What's P dot? P dot is a force, right? It's a change in momentum. D is basically F is equal to P dt. That's equal to basically d by dt of E over C, right? And so this is just going to be equal to I times A over C is the force that you absorb on a perfectly black surface. If you reflect it, the only change is that you get a factor 2 here, because basically the change in the momentum goes from this to that. All right, that's just the only thing you got to worry about. Okay, but I'm not going to worry about that right now. So that's just I times A. Okay, so now if I divide by A, right, the force over area, that's just a pressure. Okay, so basically P rad, which is the radiation pressure, is equal to I over C. Okay, and then F rad, which is radiation force, is just basically I A over C. Okay, all right, so that's basically the important bit of it. Now we're going to use it for one important thing, which is basically, or consider a following example of a solar sail. Whoops, sail. Okay, so few important tidbits. First of all, solar constant is roughly 1 kilowatt per meter squared at Earth. Okay, so if you're at Earth, midday sun, all right, it's roughly about 1 kilowatt per meter squared. Okay, it's a little higher than that, right? But average over is about 1 kilowatt per meter squared. Okay, so what we're going to do is consider the following. So let's imagine you have a solar sail. So there's a mass here. This is going to be 0.1 kilograms, a really tiny mass. And then attach it, you have a gigantic solar sail here, which we'll assume is almost massless, all right? So I'm basically going to make this a square sail, right? Just for make it simple. And I'm going to make it 100 meters by 100 meters, right? So basically, football field in space, all right? Right, perfectly reflecting super light material, pulling this thing along. All right, I'm going to calculate what the force is going to be. So light comes in, light gets reflected away. The force radiation is going to be equal to, now it's going to be 2, that's from reflection, times IA over C, right? So basically it's 2 times the solar constant, which is 1,000, divided by C, 3 times 10 to the 8, times basically the size of the sail, which is 100 by 100, so 100 squared. Okay, so let's go ahead and compute this thing out. This thing works out to be about, this is 10 to the 4, 10 to the 3, that's 10 to the 7, divided by this thing. It's essentially 0.6. Let me make sure I get that right. Right, sorry. It's 0.06 newtons, roughly speaking, 0.066, whatever. Okay, and then the acceleration due to radiation is then basically F rad over m, right? 0.1 kilograms, right? That's basically 0.6 meters per second squared, right? That's a fairly respectable thing. It's not anything compared to Earth's gravity, which is something like 10, right? Okay, so if you want to ask how long to reach 10% of speed of light, okay, so that's V is equal to did I do 10%? I chose I chose 1%. Okay, that's going to be equal to 0.01 times 3 times 10 to the 8, 3 times 10 to the 6 meters per second. All right, let's see how long that would take. Okay, so V is equal to A times T, which is, we just determined what that is, 0.6, right, times T is equal to 3 times 10 to the 6 meters per second, right? And then, so it turns out that in that case, if you divide this thing out, this is roughly T is equal to 5 times 10 to the 6 seconds, about 2 months. Right? That's actually not bad. Okay. So how far does it travel in this time? That D is equal to 1/2 AT squared, right? That's basically something you got before. That's 1/2 0.6 times T is 5 times 10 to the 6 seconds squared. So that turns out to be about, if you work this thing out, it's 3 divided by, wait, hold on, let me get this right. It's going to be something nasty. Well, I'm going to write down what the answer is. 7.5 times 10 to the 12 meters. This is about 50 AU. So basically, roughly distance to Neptune. Actually, I think it's longer than that. I think it's, Jupiter is 5 AU. I think it's probably 4 times the distance to Neptune. All right. Okay. So that's basically why this actually never reaches this velocity, because by the time you get out to Neptune, the solar radiation has decreased substantially, and so basically you don't actually reach that velocity. But it's good to know basically that's something that is possible, right? Now, this is also, also partially the reason why a few years ago this Russian investor wanted to plow $100 million into something called Operation Starshot, right? And the way that works is that they were going to build this giant laser, okay? And this laser, going to shine this laser beam at a tiny solar sail, all right? That was going to basically carry a payload that was weighing about the size of an iPhone, okay? So something like a few hundred grams, maybe about 100 grams or so, right? It's about a tenth of a kilogram, basically what I just stated right there, right? And there was going to be so much power hitting this thing that it was going to be, say, shoot it at something like 20% of speed of light in about not a few seconds. I think it's going to be, why did I say how long it's going to take? I said it was going to take about, I don't know what it said it was going to take. Right, in 2 minutes, right? So it's going to shoot it to the speed of light in about 2 minutes or so, right, on this thing, okay? And it was just some absurd amount of acceleration, basically. But it turned out that that acceleration is something that bullets and artillery shells experience all the time, and we know how to build electronics for that sort of thing, okay? And we're going to basically accelerate this thing to some huge amount of power, and you could basically estimate how much energy that would take. And it turns out that it's not super crazy, right? The only thing he's got built essentially a Death Star laser in the middle of a desert, right? Okay, well, I think that's it for today. I think, and that is actually it for the semester, is that, right? And so basically, starting next week, what we're going to do is going to do some review of everything and get ready basically for everything else. Okay, well, thank you very much.